So for this video I'll be working through question 4 of the level 2 physics 2015 mechanics exam. So, question 4, circular motion and torques. Explain why the ball is accelerating even though it is swinging at a constant speed. So there's two sort of criteria for acceleration. One is it's either changing speed, the other is it's changing direction. So it's not changing speed, but it's changing direction. So the ball is constantly changing direction, which means it's accelerating. Means it's accelerating. There we go. So simple as that. The length of the string is 0.75 meters. It takes 0.84 seconds. The ball go around her head once. Just for if I haven't read it, she's swinging a ball around her head. That's what she's doing. Calculate the acceleration of the ball. First and foremost, it's probably going to help if we have the velocity. So velocity is just change in distance over change in time. I always go back just to the definition of it. Change in distance, one whole full circle. Formula for a circle is 2 pi r. So the distance it travels, 2 pi times r, which is 0.75, divided by the change in time. What's the change in time? 0.84 seconds. It gives it 84 seconds, and that is equal to 5.61 meters per second negative 1. Notice I haven't rounded yet, even though I should be in 2SF, but I'll round at the end. Sweet. So found the velocity. Your given force is equal to mass velocity squared over r. That's given to you on your formula sheet. I want to derive the acceleration because you're trying to work out the acceleration, not the force. Derive it from this, so it's also equal to just normal mass times acceleration. So notice we'll divide both sides by mass. So we're going to divide this side by mass, which cancels it out. Divide that side by mass, and we get left with acceleration is equal to velocity squared divided by the radius. Oh, look at that. So we had the velocity up here. So that's equal to 5.61 meters per second negative 1. Bracket, you square that, divided by 0.75, and that is equal to 42 meters per second squared, or 42 meters per second negative 2, whichever you fancy. And notice two significant figures, so my answer has to be in two significant figures. In fact, I'm going to write 2SF, even though you shouldn't really write this in your paper. But yeah, two significant figures. Right, name the force that causes the ball to accelerate as it goes in a circle. Explain why the force causes the ball to accelerate. So this is probably the most common misconception or common thing I see with all of my students, and they seem to think, well, once you learn about the centripetal force, they confuse that for an actual force. So I'll write the answer first. So it's the tension force. The tension force is what makes it go around in circles. Centripetal force is literally Latin for center pointing force. It's not an actual force, it's just a name for something. So the tension force, the tension in the string provides, let's spell that correctly, provides the centripetal force, which is, well, like I said, Latin for center pointing. So it's the tension in the string provides centripetal force. This tension is unbalanced, obviously, otherwise it wouldn't be accelerating. Unbalanced, which causes the ball to accelerate. Accelerate. There we go. And if you really think about the fine details about swinging a ball around your head, you can't actually have the center fixed. So the center has to move like that there, which means you're providing a force on the string. So you're making the unbalanced force. in the example they give, they sort of assume the centre is stationary, which is probably what confuses a lot of students, because you can't have a stationary centre, otherwise you won't be able to provide an unbalanced force. So that's possibly where the misconception comes from, but that's just a guess. Right, next question. This is a talk question. Thus was in the question. Circular motion and talks. Here we go. Janet's study table has 2 panels, one at each end. Janet has a pile of books on a table. Use the details below, yada yada yada, to find the support force of A. So what we're trying to do is find the support force of A. So the talks are around here. A equal to the talks around here. Yeah, because they're in equilibrium. They're not moving. Sweet. Torques around A is equal to torques around B. This is not always the case, just happens to be the case for this one here, because it's not moving. In fact, I think it is. I need to double check. I always just assume these things. Right, so torques around A are whatever force. So torques around A is if we, it's almost if we produced it from here. So if we had a force, so here is force A times that distance here. That would give you the torque. That would give you a torque around A. It's the same as the torque around B. So we're assuming that torque is the same. I'll just sort of work through it, and you hopefully be able to work it out. So F times A, I'll put that there, times the distance is 1.5 meters, because it's 1.5 apart, equals torque around B. Right, torque around B. We have the books, so we'll start with the books. So we got 7.4, but this is just a mass. We need to times this by gravity, 9.8, to get the acceleration, get the force, because it's mass times acceleration, get the force, times the distance is 0.45, 0.5, yep. And you just add torques together. Next one, mass of the table, 37 times 9.8. times, now this is where the trick comes in. Table is uniform, so if it's uniform, the center of mass is going to be in the middle. So here's our center of mass, 0.75, because it's the same density all the way through, not thickness. Well, yeah, density. Well, it is. It's the same density. It would be incorrect to say thickness. Times 0.7875, because it acts at the center. Here we go. So that happens to equal force times A times 1.5 equal to, once you calculate all this out in your calculator, 304.55 Newton meters. So force on A is equal to 3.455 divided by 1.5, and that is equal to 203 newtons. But 2SF again, can't be 203, it's got to be 200. Well, it's got to be 200, because these two here are our first two. You know, this is to 2SF, so it stops here. Everything past here we can't ever know, or it can't be accurate to, so it has to be 2SF because we're given it here. And that seems reasonable, and that is the answer. Here we go. If, for example, there was mass over here, some over here, so the mass is over here, they're still torques around B, but they just end up being negative because they're going the other way. So as you notice, I just made everything positive, and then I just pretend. So to work out what the force is here, you work out what the torque is, and then you work backwards from there. So once you got the torque, you think, well, if I just got rid of the books, if I got rid of the table and just had a length of wood with no mass whatsoever that you could push here, you know, how much would I need to push to generate this amount of torque around here? And then that force is the force required to generate that torque. And then if you flip the argument backwards, so let's go from, if I want to generate torque around here, how much force do I need to push over here? And that happens to be the force of A. Yeah, I think I've done this a bit wrong, but that's alright.